back, we're gonna knock up memory, causality, and stability. Which this, if you're watching this module 1, we don't have to do this yet, but we're gonna go over because it's easy. For problem 1.27c. So let's start with causality. So if a causal system cannot anticipate. So if we want to figure out y of t, it can't depend. It can't depend on some future value of t, right? So let's look at what we have. We have y of t is equal to the integral from negative infinity to 2t times x of tau d tau. Now, if we look at our bounds of integration, that's kind of giving us, so here's our time axis, right? And here's 0 right here. Oh, we don't even need a vertical there. We have a 0 right here, right? And then here would be 1, and here would be 2, and here's -1, and here's -2, and dot dot dot. Everything's going off. And let's say we wanted to look at time t equals 1, right here. So we want to look at y of 1. Well, that's going to equal the integral from negative infinity, and then we want to go to 2 times t, which is 2 times 1, which is 2, x of tau d tau. So we're looking at y of 1, right? But we need to integrate from negative infinity, from down here to here. We need to integrate to here. Which, if we're integrating to here, we're anticipating the future, we're integrating past where we're actually looking at on our time axis. So this is a non-causal system because we have to look into the future. So the system is non-causal. And I'll write that out one more time just so we can see it. So we just evaluated that y of 1, and we know we got to go to t equals 2. And I'll just write this little, we need x of 2 for y of 1. So it's non-causal. Now, let's tackle memory. All right. Now, I guess I shouldn't have deleted that or erased that time axis. If the system is memory, if the system requires memory, or a system, let me say it like this, a system that does not require memory only depends on that current value of t. And we can clearly see just from integrating, I mean, when we integrate, we need to know our past values of x of tau. If we need to know our past values of x of tau, then we have to, that just, it's pretty clear that means that it requires memory. And when you take, I don't know if you haven't taken 334 yet, but there's something called an integrated circuit, and it involves a capacitor, and that's because a capacitor stores electrical energy, and that storage of electrical energy provides us an ability to look at what has happened in the past. So I guess I can draw that little time axis again, right? Here's t, and here's 0, and here's 1, and here's -1, and then dot, 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 dot. If we're looking right here, we're looking at y, well, we need to integrate back this way. So the system requires, can't spell, requires memory I dot E not, I'm not going to say this word, but I'll write it. So we have a no, we have a no, and then let's take a look at stability. Now for stability, what stability is saying is that if we put some bounded input into the system, do we get some bounded output out? Let's say that x of t is equal to 1 for all t. So x of t is equal to 1. That is a bounded input, right? It is not blowing up to infinity. We're just saying x of t is equal to 1. So that's a bounded input. Then we can do our integral, and we'll have y of t is equal to the integral from negative infinity to 2t times d tau. There's that 1 in there, it's implied. So then we'll get tau times tau evaluated at 2t and negative infinity, and we take the limit, so then y of t is equal to the limit as b goes to negative infinity of tau to b, and we get 2t, or we have to put the limit in there again, and we'll have 2t minus b. And when we take this limit, then obviously we're gonna get that 2t minus a negative infinity. Well, that gives us a positive infinity. So we do not get a bounded output. We put a bounded input in of x equal to -1, and what we get out is we get an infinity, and that means our system's blowing up, and that is not a stable system. System is not stable. All right. Thanks. Hope helps.